Good afternoon, everybody. Thank you guys for those that are connected online. Thank you for all the all the guys that are in the auditorium. Thank you so much to Ingo, who took care of the technical arrangements with Aaron and Andrew, of course. So thank you to them. So this is an experiment. This is a test session where we have this first in auditorium format, and we believe it's a good idea. People will be able to clap hands and raise their hands, really like as if it was a presential seminar, even though the speaker today is online. But we're very excited with this new format. And so for today, I have the pleasure of introducing Professor Rafael Chaves. Rafael Chaves is a very good and old friend of mine. We met each other while doing our PhDs here in Brazil. And Professor Rafael Chaves has had a very successful trajectory after postdocs in Barcelona and in Köln, in Germany. He came back to Brazil, to the International Institute of Physics in Natal, which is perhaps one of the best places to work in Brazil in several aspects. And he's a group leader there of the Quantum Information and Quantum Matter group. He's also a professor at the Federal University of Rio Grande do Norte. And he has had his grantee of several agencies and both in Brazil and abroad. He's been a grantee of the FQXI agency. He has grants of the Templeton Foundation now. He's a grantee of the Serra Pilheira Institute now, which is a sort of Brazilian version of the European Research Council. So it's really a prestigious researcher. And yeah, we have the pleasure of having him here today. He's our first South American speaker in our seminar series, right? In fact, he's our first speaker, which is non-European or non-North American, so to say. So it's really a pleasure to have you here, Rafael. So please go ahead, proceed. People may raise their hands and ask you questions during the talk. And yeah, we will let you know. We will tell you. Okay. So thank you so much again.
Yeah, perfect. Thanks, Leandro. Well, as you said, like we are longtime collaborators and friends. So it's I've heard a lot about the institute. It's a pity I cannot be there, but well, who knows next year, right? But in any case, it's a pleasure to be talking to you here today. So I'm going to discuss something that we've been working in my group for 4 or 5 years now. It's a topic that I believe most of you will not be really aware of. So the talk will be mostly basic, trying to give you an overview of the field, the main tools and results. But of course, if you have technical questions, just interrupt me at any time, okay? Yeah, so let's start with something that has little to do with quantum physics. That it's the fact that if we make a quick search on the internet, we are going to find plots like this. So where we are basically seeing like the ice cream sales and consumption over the different periods of the year, like the different months of the year. And we see that this ice cream is correlating quite well with a lot of different variables, shark attacks, violent crimes, forest fires, drowning deaths. So at first it might seem a bit weird, right? Can ice cream be such a terrible villain, like responsible for all these tragedies? But of course we know what's going on here. And this peak here around July, August, that it's the summer in the northern hemisphere is giving us a clue. And of course, as the statisticians would never let us forget, correlation is not causation. So it's clear that like sunny summer weather is like the common cause both for like a higher number of ice cream consumption and like things like sunburn. So in retrospect, this is almost trivial, right? But the point here is that this mantra of statistics, correlation is not causation, has gone too far. And this is well illustrated by this article some years ago called The End of Theory, where the authors say things like a correlation supersedes causation. So, science can advance without coherent models, unified theories, anything at all. Correlation is enough. Just throw the numbers in the biggest computer centers we have ever seen and let the algorithms find patterns where science cannot. So if this would be true, it would be the end of our scientific careers. We could just enjoy life and let the computers do the rest. But of course, nothing could be further from the truth. And this is well illustrated by this paper of Kalud and Longo, where they took like many different kinds of very large databases and shown that they tend to contain arbitrary correlations that appear only due to the size and not the nature of the data. So their conclusion is that most correlations are spurious in the sense that too much information tends to behave like very little information. So we have these two pictures here that people working in machine learning certainly know. We can easily use neural networks and different techniques to like recognize chihuahuas or these wrinkled dogs, but we can also very easily confuse our machines, like throwing spurious correlations at the data, like these muffins or these towels, and the machine will not be able to like see the difference in the pattern. The point here is that if we look enough, we or like machines, we are always going to find patterns where there is only noise. So data cannot be interpreted in a theoretical vacuum. Like what we do is not that we take a mountain of data, like random experiments, and we try to find something meaningful there. We start from a hypothesis, and only then we select and perform like experiments that are going either to confirm or falsify our hypothesis. The problem here is that how can we start with a hypothesis? If from the data I only get correlations, then it's a bit like the chicken and egg argument. Where should I start from? And that's exactly the why causality theory has been introduced, and it's what we are going to see in the rest of the talk. Like, so this was just like the motivation. So what we are going to try here is to go against the statisticians and say, look, we can go beyond the correlations from the data. So for that, like in the first part of the talk, I will introduce you like gently to causality theory. We are going to see concepts like interventions and instrumental variables. In the end, I'm going to talk a little bit about that, but just today, a Nobel Prize has been given to this tool here in economy. So it's a very nice, it's a very hot topic now. And then we are going to see that this causality theory is really like a very powerful framework that has been used in a lot of fields, but we are going to mess it up by throwing quantum effects into the picture, and then many things will change. Okay, so causality theory. In the end of the 80s, like beginning of the 90s, like researchers in artificial intelligence, they were trying to teach their machines, but they were having problems. And the problem, as we are going to see, is that machines, and still these days, they are trying to only find correlations, patterns in data. But what people like Judah Pearl, they realized is that the real learning, they should go beyond like the simple pattern and really understand what was causing what. So that's the historical background of causality. And to understand how can we do that, we can go back in time, like 50s, 60s, when Reichenbach, who is a philosopher, physicist, and mathematician, he wrote many books, and he stated in one of these books, like something that we call now his principle, basically going against the mantra of statistics and saying that there is no correlation without causation. In the sense that if an improbable coincidence has occurred, there must exist a common cause and or a direct causal influence between these apparently coincident events. So let me give you an example. Suppose there were no pandemics, I would be there in Abu Dhabi in this nice research center for a week, let's say at least. And then every day in the morning, I would grab my cup of coffee and sit in front of two rooms. And I would see that the lamps in these two rooms, always when I look at, they would be either off or on, off, on, off, on. So perfect correlation between both of them. It seems indeed like a very unlikely coincidence that random people would always enter and leave the room at the same time, like turning off and on these light bulbs. So there must exist some sort of causation involved. The question is which kind? Could be like a direct causation. One event is causing the other, like because of some bad wiring in the wall, like whenever we turn on and off the light in one room, this causes the other lights to be also off or on. Or could be that the wirings are fine, and actually what's going on is that I have a third event that potentially is not directly observable, like some short circuit, some fluctuations happening outside the building that are responsible for these correlations that I observe. So just one question, can you see my pointer? Yeah, okay, perfect. Okay, so this is very simple, of course, but illustrates well the task that we have here. Like we have empirical data, lights that are on and off. Potentially, we have some effects that we don't directly observe. And from that, we want to infer what's causing what. Of course, this fits very well in the artificial intelligence setting, in the sense that we have a robot like a machine that has sensors, is able to sense and interact with its environment. And from this data, it's able to learn something about this environment. Where learning here means not only seeing correlations between the events, but really trying to decide what is causing what. Okay, so how can we do that in practice? First thing we do is that we encode the causal relationships between a set of variables in a causal structure that can be represented by what we call a directed acyclic graph, a DAG for short. So each node in this graph represents variables that are relevant for the process, where some of these variables that are represented here by circles, we have empirical access to them, and some other variables like these lambdas, they are latent. We would call this in quantum physics like they are hidden variables, in the sense that we assume that they are present or that they are potentially present, but we do not know. We don't have empirical data about that. And the point here is that the causal relations between these variables, they are encoded in these directed edges. The crucial aspect of this formulation is that causal relationships, they are encoded in the conditional independencies that are implied by a given DAG. So what I mean with that? Let's look at these two variables here, lambda1 and lambda2. They do not have an edge arrow from one to the other, nor there is a third node like lambda3 that acts as a common cause to both of them. So this means that these two variables in this model here, in this causal model, in this causal structure, they should be causally and statistically independent. Like they should follow this factorization law here, independently of the specific mechanism. Like it could be that like the response functions of A, they are nonlinear, they are whatever. They could be anything, but independently of these specific mechanisms, these two variables here, they should be independent. So just to connect with something that we say in quantum information, this is like a device-independent formulation. We are working at the level of the data and not on the level of like the specifics mechanisms of the variable. Another possible conditional independence here, it's the fact that A and B, in general, they are going to be correlated because they have a common ancestor, this lambda1 here. But if I condition on lambda1, the correlations between A and B, they should screen off, they should disappear. I have like a very efficient algorithms that, given a causal structure, given a DAG, they can list all these conditional independencies. That again, they hold information about the causation. So let's see now how can we use that to solve the causal inference problem. So let's say I have the data about these 6 variables. So I just run my experiment like many times. I have this probability distribution involving these 6 variables. And from that now I can test my causal hypothesis. Let's say for some reason I believe that the causal hypothesis, the mechanism, the causal mechanism that is generating my data, it's a causal structure like that. What can I do now? I just check, take my data and I check if all the conditional independencies that are implied by this model are fulfilled or not. If one of them is not fulfilled, then I can be sure that this causal structure is not the one generating the data. And if I pass all the tests, then I have a good confidence that, well, at least I can say that my hypothesis is compatible with the data. So this is very nice, because now what I'm saying is that really the statisticians, they were wrong. Like from data, I can say something about the causation. I can falsify or confirm compatibility with the causal hypothesis. But there is a problem. And it's the fact that not all the variables in a given causal model are going to be always observable. And then the problem becomes a bit more complicated. Can you still hear me?
Yes, we had a little interruption. I don't know whose connection was it. At least I got a little interruption here, but now I think it's good.
Okay.
Yeah.
Yeah, like we have a rain here, so sometimes my internet gets bad with rain. Let's see.
Okay, go ahead.
But I have my
That's
phone
great.
here, so I can try to connect if it's bad.
No, it seems to be gone now. It's going well. Great, great, Rafa. Thanks.
Okay, so in practice, like many times, we don't have empirical access to all the variables. So let me introduce a scenario that I guess most of you know, that it's related to Bell's theorem. So what's Bell's theorem? We are going to impose a causal structure to our quantum experiment and ask if a classical description of this causal model is compatible with the data that we generate in the experiment. So what's the causal structure? We have two distant labs, Alice and Bob, and in between them we have a source of particles, like that it's represented here by lambda. And we treat this source as a hidden variable for many reasons. Like first, we might not have access to all the degrees of freedom of the source. Or like if you are Einstein, you would believe that quantum mechanics is not complete. So there might be some degrees of freedom that we don't have access to by definition. So we are going to treat this source as a hidden variable, like something that we presume exists and it's there, but we don't have access directly. So what we have access, it's like measurements, like form on the states that are being generated by the source. So Alice and Bob, they receive their parts of the system. They flip a coin X for Alice, a coin Y for Bob. They decide which observable they are going to measure in that run of the experiment, and they get the outcome A and B. So in this kind of experiment, we have what we have observable. It's the probability of A and B given X, Y. So like the correlations between A and B, given that Alice and Bob decided to measure some observables X and Y. The problem here is that all the conditional independence, or most of them, they, for instance, like the free will assumption will impose that X, Y, and lambda, they factorize, so they are independent. The locality assumption will imply that like what Alice is seeing in her lab, because Bob is so far away, should not depend on anything that Bob is doing in his own lab. And then you see that all these conditional independences that hold information about causation, they happen at the level of the hidden variable. So this means that I cannot test these guys directly. But what I can do, I can eliminate them from my description, like something that I can do mathematically using quantifier elimination. So like in practice, I just plug in this here into this probability distribution that it's the one I observe, play a little bit with probability, and in the end of the day, what I see is that any probability distribution that it's compatible with this causal structure, or at least with a classical description of this causal structure, should be decomposable in this way. That it's what we call a local hidden variable model. And this local hidden variable model imposes constraints to what I can observe in my experiment. So anything that is compatible with this causal structure should fall inside this gray region here, that it's limited by what we call Bell inequalities. So what are Bell inequalities? Are nothing else than the consequences on the observable level of imposing a causal structure to my experiment. And this is very nice, because now if I have a experimental point, where experimental point means I have a probability distribution, P of AB given XY, and I see that this point falls outside this gray set, meaning it violates a Bell inequality, then I have an unambiguous proof that I'm falsifying this causal structure. Or at least I'm falsifying a classical explanation of this causal structure. So this is Bell's theorem under this new lens of causality, okay? So now let's try to use this nice framework to solve the most basic question we have in causality. And then we are going to see that we need to introduce this idea of intervention. So if you have any questions, please just interrupt me, okay? Okay, so the basic question is this. I have two variables, A and B, and I see that they are correlated, like smoking and cancer, let's say. Now the question is smoking responsible for cancer, or perhaps there is a third node that I do not directly observe, that it's causing these correlations between A and B. So like smoking could cause cancer, but actually what would happen is that this data that we are seeing was taken from people that were kids in the 60s and in the 50s, let's say. They were exposed to like the radiation of these TVs that could cause like cancer in them, like mutations or whatever. But back then, like it was very common to have like advertisements saying that smoking was cool. Doctors would smoke like the Marlboro Man. So people would have a higher probability to become smokers and at the same time to develop cancer. The question is, given that I see these correlations between A and B, how can I decide this? It's this model or this model. And in this very simple question, I cannot resolve it. Why? Because these two models, they are indistinguishable. Both of them, they don't imply any non-trivial Bell inequalities that I can use to falsify any of these two models. So we have this very nice framework, but it doesn't work for this very simple question. So we have to introduce something more, that it's so-called intervention. So now, instead of passively see what's going on, like let people smoke and see if they get cancer later on or not, I intervene in the system. So now I intervene, I take two groups of people, put one in a cage, the other one in a different cage, and I force one of these groups to smoke like 2 packs of cigarettes every day, and the other one to like eat, I don't know, kombucha and whatever, like healthy, and see what happens afterwards. So basically what an intervention is doing is forcing a variable to assume a value independently of the rest of the universe. By intervening on A, something that mathematically I represent here by do A, I'm forcing A to assume a value, is equivalent to breaking it's equivalent to break all the incoming edges to this variable here. And the crucial thing is that the probability of B, given that I observe A, it's different from the probability of B, given that I do A, given that I force A to assume a value. And that's clear, and it's clear why this happens, right? Because if I force A to assume a value, I'm breaking this link here now, and I still see correlations between A and B. In this case, I can be sure that this can only be due to this arrow here. So if I force A to assume a value and I still see changes in the probability of B, now I can be sure that this is due to some direct causation. And in fact, this naturally introduces a measure of causality. That it's what we call average causal effect. Like I'm basically seeing, depending on what I do on A, if I see shifts in the probability of B or not. Okay, great. So it seems we solved the problem, but we cannot force people to smoke. Like interventions are a nice theoretical tool, but that in practice, they cannot really be used all the time. Like it's clear that in many instances, they are not a good tool. So the basic question still remains: can we infer causality without the need of forcing people to smoke, without the need of interventions? And then we come to the instrumental variable, that it's one of the most beautiful things I've ever seen. I hope you will agree with me in a few minutes. So what's the idea? I have the same scenario as before, correlations between A and B that could be due to this common cause or could be due to this direct causal influence from A into B. And what I do now, I introduce an extra variable, that it's the instrumental variable X, and I assume that this variable is independent of lambda, it's independent of this and
Rafa,
and
Rafa. Rafa,
directly and
Rafa,
yeah.
can you hear me?
Can you hear me?
Sorry, we lost you for a second. Can you start again the explanation on the instrumental DAG?
Yeah,
now
I will only open the door here. Maybe the connection gets better.
Okay. Thank you.
Is it okay?
Yeah, it's good. Just the last part on the instrumental DAG.
Yeah, so this instrumental DAG, like it's basically saying that this variable, it's independent of lambda, and it affects A, and via A, it should affect B. But we are not doing an intervention anymore. We are just looking at the observational data. We are looking at the correlations of between A and B, given that I observed X. So what could be this instrumental variable? Like, could be a government that is going to tax more or less the tobacco in the country. So if the price of the cigarettes are 50 cents, more people are going to smoke, and they're going to smoke more. So if there is a causation between A and B, we should also see an increase in the number of cancers in the country. Or if a cigarette costs $100, less people are going to smoke, and they're going to smoke less, so we should see a decrease in the number of cancers. So I mean, we are not forcing people to do anything. We are just introducing a new variable that has some causal effect over this variable A and seeing what happens. And why this helps? Because in this very milestone paper here from Balk and Pearl, they proved the following. That looking at this observational data here, P of AB given X, they can put lower bounds to the average causal effect. But remember that the average causal effect, it's an interventional quantity. So what I'm saying to you is that simply from observations, from seeing if people smoke more or less, depending on the price of cigarettes, I can infer what would have happened if I forced them to smoke. So I can indeed infer causality simply from observations. So you can imagine this is really powerful. It's used like widely in economics, in medicine, biology. Now it started to be used also in quantum physics. Okay, so this is very nice, but we still have.
Rafael, can I ask something?
Sure, please, yeah.
So how do you make sure that you are that this X is only acting on A? Or in your example, let's say the government is taxing now on cigarettes, and then I could say, okay, now people, they don't change their cigarette behavior, but as they pay more money on cigarettes, they have less money for other stuff, so they can't use the car anymore. Now they start using the bike, and therefore their health improves, and they get less problems with their lungs, right? So how do I make sure that there are not additional nodes which are then wild net and everything is wildly influencing each other?
Okay, so this is a very good question, and I hope I will solve with my next slide. So basically, what you have to guarantee is two things: is that X does not have a direct causal influence over B, like like people, oh, the government is making the cigarettes cheaper, so they start to develop cancer even if they don't smoke. Of course, this seems very unlikely in this example, but it could have other ones. Or in the second thing that it's really more complicated, and it's related to what you asked, you have to guarantee that your instrumental variable it's independent of any common causes between A and B. Like, for example, this common cause could be the fact that they become healthier, like they start to go with the bike, and perhaps they are going to smoke less. So what you have to guarantee are these two things here: that X does not have a direct causation over B, and that X it's not correlated with this potential common cause between A and B. And how you do that in practice? Then Pearl, again, he realized that if the causal structure that you are using, it's really this one, so meaning if you really have an instrumental variable, the data that you generate in your experiment should respect constraints. These constraints, Pearl called the instrumentality inequalities. This is what we would call Bell inequalities. So what is a Bell inequality? It's like a consequence of imposing a given causal structure to our experiment. So you take your data. The first sanity check that you have to do is to see if your instrumental inequality is violated or not. Because if it's violated, then you can be sure that one of your assumptions are false, and you should not get any and you should not apply these bounds anymore because they involve explicitly like these two assumptions. Does this solve your question?
Yes, super, fantastic. Thanks a lot.
Okay, really so yeah, we have ways of testing that we have a good instrument.
Rafa, may I ask myself a question?
Yeah, please.
Ignacio. Yeah, if I think of the examples of Bad inequalities, indeed, if a Bell inequality is violated, I know for sure that it is has a quantum origin. But if it is not violated, both ideas are compatible. Okay.
Yeah.
So something similar happened here. Is these inequalities you're writing? I don't really understand what they mean. Max of I don't know whether if this is fulfilled, it means that you are discriminating totally between two possibilities, or it's only in certain cases that you can discriminate.
So this is a good point. Like you can never, like if you don't violate this inequality, you cannot really be sure that you have this causal structure. The only thing that this is showing is that the data you have at hand is compatible with this hypothesis. So the point of causal inference is that we can only falsify causal hypotheses. We can only falsify causal models. But if you don't violate them, then I mean it could be any of these models here. But like I mean, if you don't have data that can be used to falsify this model, then you can, like with a good confidence, trust that indeed you have a instrumental scenario. But you are totally right. Like you can only falsify.
To be clear, let me understand it better. Typically in Bell inequalities is when the correlations are weak. Typically you cannot distinguish between classical and quantum. So this is in general true. When the correlations are weak, those are the worst scenarios in terms of discriminating causality.
Yes, like typically to violate these inequalities here. Well, I mean, actually, it's a trade-off, because like a way of violating this inequality would be like if X has a very strong dependence on, if B has a very strong dependence on X and depends little on A. So I mean, there are different ways of violating these inequalities. They like, so you don't need to have a strong correlation between A and B or between X and B. Like there are really different trade-offs here. It's not as simple as in the Bell case, I would say. Okay.
Okay.
But let me just add a comment.
But it's true that for the Bell case, well, Jose Ignacio is right that in the Bell causal structure, when you have little entanglement, it's difficult to violate, right? The thing is that here it changes for this one,
depends, right? Like if you have detection inefficiencies, actually little entanglement is better than a lot of entanglement. So it really depends on the experimental constraints. In this sense, I mean that it's not clear. It really depends on the experimental constraints you have. But let me just add something, like the violation of a Bell inequality does not prove non-classicality, because you have to close all the loopholes. And there is a loophole that in principle it's unclosable, right? That it's the measurement independence or the free will loophole. I mean, okay, just like to say that there are many plagues here in this kind of causal setting. So you always need to have some assumption. Okay, great. So the point here is that we have this causality building has two pillars, like the fact that we can estimate the effect of interventions from observational data, and the fact that at least to some extent we can check if we have a good instrument by checking if these instrumental inequalities are violated or not. But since Bell, like 64, we know that our most basic notions of causality, that are the notions that are entering here in these two pillars, they fail to describe quantum phenomena. Then the question that we started to ask some years ago is if we can shake these pillars with quantum mechanics. So in the second part here of the talk, I hope I can finish in time. I'm going to explore a bit of the of how quantum correlations can change this picture. The first thing we can do, we can ask if we can violate instrumentality test, if we can violate an instrumental inequality. So let's think of Bell. What is Bell's theorem about? I'm imposing a given causal structure to my experiment, and I'm asking whether a classical description of this causal structure is compatible with my data or not. So I'm going to do the same here with the with the instrumental DAG. I am going to impose this causal structure to my experiment and ask if the data that I can generate in a quantum experiment is compatible with a classical description or not. So what I mean with a classical description, this node here is not directly observable. So in a classical description, I would assign this to random variable that even if I cannot observe it directly, I can assign to it a probability distribution that it's well defined, P of lambda. And then A should be a function of X and lambda. This is here. B should be a function of A and lambda. Okay, so this is the classical description. It's the analog of a local hidden variable model for this causal structure here. Then we can ask now if we can violate the constraints implied by this description. So the simplest case would be when X, A, and B are binary variables. They can assume the values 0 or 1. This would correspond to a sum of these inequalities. There are proofs that inequalities, they cannot be violated by a quantum mechanics. So we had to look for inequality. And the binary
Rafa,
X now can assume up to 3 values. So you see that this inequality like we have here. Yeah.
Sorry, Rafa, can you repeat that? We just lost you for 20 seconds, for 15 seconds.
Oh, sorry. Yeah, it's a pity that my internet bad today. What I was saying is that to find a violation of this classical model, I need
It's unstable. Okay, now we did lose you, Rafa. Well, hold on. I'll write him a message. Oh, I guess he's gonna change. He's gonna change connection. I guess he's gonna connect through his mobile phone. In fact, yeah. Let's wait for.
Let me ask you.
Yeah. Sorry. I'm sorry.
Because you know everything. So, but I think let me understand if.
Please.
I take Bad inequalities and I have a combination that has to be less than 2. No? If all the correlators are close to 0, there is no way.
Can you hear me now?
Okay.
Yes, we can hear you now, Rafa.
So
you change connection
to my phone now.
All right.
Yeah, I'm connected to my phone. Let's hope it works better now. Sorry.
Okay. Yeah. Jose Ignacio was just asking a question. Jose Ignacio, go ahead, please.
No, I was refining the question I made before because I said, look, this equation you have in the transparency. If all the correlators, well, in this particular case, you have individual B, B, and A. But if in the Bad inequalities is that you only have correlators.
The two-body correlators.
If they are all very small, you can never violate a number. No? If they are close to 0, minus 0.1 plus 2.02 will never be.
Yes,
okay?
That's true.
So it is directly the fact that you can discriminate between models of correlation of causality is directly depending on the large correlations. Will never be discriminate. You can never discriminate in the case of a small correlations.
Yeah, well, so I think that what Rafa was saying is that in the case of the CHSH of Bad inequality, this is clear, and I agree with you. But then there's the question of classical versus quantum correlations too, right? You can have correlators being big because of classical correlations, or being big because of quantum correlations. And I think that what Rafa meant here is also this inequality is different, right? Because you have like these single body terms too. But I agree with you, Jose Ignacio, that correlators
Yeah, the
need to be big,
marginals, yes.
but you can have classical correlations too.
If they are small, in a way, you are lost. There is no way to discriminate whether there is causality or not.
True. Yeah, I think so.
Yeah. In general, like well, we have some cases that fall out of that, but they are perhaps like anomalies, let's say. Okay, so let me try to go faster here.
Rafa, just one. But now, can you go to presentation mode, or do you want to do it like this now?
Sure. Yeah.
Thank you.
Yeah.
All right. Thanks. Great. Yeah.
Okay. So the point now is that we can violate this inequality, and by that, like I'm going to impose this causal structure to my quantum experiment. So what means a quantum experiment here? I have to quantize at least one of these nodes, and there are different ways I can do that. Here, I'm going to do, let's say, the simplest one that is closely related to Bell. I'm going to quantize this hidden node here. Instead of having a random variable now, I'm going to have a quantum state. So I'm going to have a quantum state rho that is shared between Alice and Bob. Alice now, she's going to measure her part of the system, depending on what's the value of the instrumental variable X. So she's going to apply some measurement operator here. And Bob is going to apply a measurement operator on his side, on his part of the system, that depends now on the variable A, on the outcome of Alice. Okay, so if we choose the correct states and the measurements here, we can find values that surpass the classical bound. So the main message here is that like this gap, this mismatch between classical and quantum description of causality is not restricted to a Bell scenario. We can also find this mismatch in different causal structures. And from a causal perspective, that's nice, because if I would find a violation of this inequality in a classical setting, this would mean that I would be violating some of my assumptions. For instance, that I have a direct causation between X and B. And in fact, we can prove that classically, the more you would violate this inequality here, the higher should be this causal inference, this causal strength between X and B. So quantumly, of course, what this is proving is that we cannot assume that this hidden variable with a well-defined probability distribution exists. So this is a proof of non-classicality, a new proof of non-classicality. Okay, but let's be a bit more precise here and try to compare now Bell against the instrumental. They seem quite different. Bell involves like 5 variables, instrumental involves 4. So like in this sense, the instrumental case, it's a bit simpler. And the Bell scenario, it's what we call a spatial correlation scenario. Like we have Alice and Bob, in principle, they can measure their systems like simultaneously. And like they have these spatial correlations between their measurement outcomes. And here in the instrumental case, we have a temporal correlation. Alice, she measures first, she gets her outcome, and depending on that, Bob is going to do something in his lab. So it's a temporal correlation. But if we look closer, we are going to see that they are strongly connected, because I can see an instrumental scenario as a scenario where the outcome of Alice is determining what Bob is going to do, relation of classicality as compared to Bell. Why? Because if we violate instrumental
Rafa, I'm afraid your connection is not working.
Of quantum theory with non-local hidden variable models, because I have this this arrow from A to B, so, and with lack, because A depends on lambda, and if the choice of Bob depends.
Rafa, we're losing you. Oh. Do you have, is it possible for you to get connected like with cable to your, perhaps it's the Wi-Fi? Yeah. I think you're muted, Rafa. I don't know if you're talking to us or if you're.
Yeah. No, sorry, I
Okay.
was talking to you. Like, it's the first time that this happens here. Very
Don't
sorry.
worry, don't worry. This is, yeah. But now you are connected to which connection? Mobile or?
To modem again. So let's hope
Okay,
it works
okay.
better.
I think it's good now. Yeah.
Yeah, it's the first time this happens. Well, okay. So the message here it's this, that like we can see the violation of this instrumental inequalities as a stronger proof of non-classicality as compared to Bell. Okay, so I'm going to be a bit faster now to not bother you with my internet connection. We can also use this violation as a resource in typical protocols we have in quantum information. So, for instance, I can use this violation to extract certified randomness from my measurement outcomes. So, like I can use this as secure quantum bits, for instance, in a protocol for quantum cryptography. So we can do that, and we see that it works. But the nice thing here is this. So in this plot, I'm showing the bit gain of the instrumental scenario divided by the bit gain that I have in the CHS8 scenario. That it's like the paradigmatic way of extracting randomness. So what's this bit gain? Is how much bits of randomness I have to put in my experiment to get a certain amount of secure random bits out, okay? And we see here, because of this ratio, like whenever this is bigger than 1, this is showing us that with the instrumental scenario, we can extract more randomness than the paradigmatic scenario, that it's the CHS8 scenario. So we see that this happens here for very high visibilities. For smaller visibilities, actually the Bell scenario seems to be better. But it's nice because it shows that a new causal structure can also, like in some experimental regimes, beat what was known to be the best case before. Let's change gears now and talk about some more recent results. Okay, so far we have focused on the correlation level of the data. So I'm only doing observations here. Like I introduced this instrumental scenario, this instrumental variable, and I'm looking at the correlations between A and B. And in this paper, they proved that in the simplest instrumental scenario, that it's where X, A, and B are binary variables, I cannot have quantum effects, in the sense that all the correlations I get from a quantum description, they can be simulated with a classical model. But this happens at the correlation level. What now if I look at the interventional level of the data? What now if I do interventions on the variable A? Can it be that this mismatch between classical and quantum reappear, even in the simplest scenario where all the variables are dichotomic? So in the classical setting, what would be an intervention? Would be like I force A to assume a value that it's under my control. So these edges here from X and lambda to A, they don't exist anymore. So I have this classical model here. And what would be a quantum model for intervention? So let's think about Alice. She's like receiving her part of the quantum system, and she's receiving this variable X here. So Alice, what she does is that, okay, I don't want to care about X, and this quantum system that I'm receiving, I'm just going to throw it in the trash and do something with my variable A that it's independent of these two variables. So quantum mechanically, what we are doing, we are tracing out the part A of the system shared between Alice and Bob. So from Bob's perspective, he doesn't know if Alice is doing an intervention, if she's measuring her system as she should. So from Bob's perspective, like this is the effect of an intervention on his outcomes. It's simply like the trace of the row B, that's the marginal state of Bob, and he's continued to use the same measurement operators that he was using before, because he doesn't know if Alice is doing the intervention or not. So the question now is, can I have non-classicality at the interventional level, even though at the correlation level, it's purely classical? And if this is the case, what this implies to the use of these classical bounds on the average causal effect? Because remember that these bounds that allow me to infer the effect of A over B, they are based on these observational data, but they, to derive these bounds, I'm using the classical description in both the correlational level and the interventional level. So if I have a mismatch between classical and quantum at this level here, this might change this causal inference tool here. And indeed, this is the case. So I'm going to give you a very simple example. Let's say I impose this causal structure to my experiment. And now I'm going to choose here as a shared state, a Werner state. So with some visibility V, I have the maximum entangled state, and with the complement, I have a pure noise. So now, from Bob's perspective, his part of the state is just the maximally mixed state, identity over 2. So independently of what is the measurement that he performs on his system, if it's a projective measurement, he's always going to observe the same. Half the times the spin will be up, half it will be down, because his half of the system is just a pure noise. So independently of what Alice is doing and what Bob is doing, the average causal effect that they should observe is if Alice do intervention in her part of the system should be 0. But what the classical bound has to say to us about that? Now we can simply choose here some measurement operators for Alice and Bob at the observational level. And we see that we find average causal effects that the classical bound will tell us that this average causal effect is positive. So you see that for some values of V, that it's this visibility here, this guy is going to be positive. So what is this telling us? It's telling us that if we use a classical bound for a quantum system, we are going to conclude that we have a positive causal effect from A into B. But if we would actually do an intervention, we would find 0. So in a certain sense, we can think of this as a quantum advantage in terms of causal effects, because quantum effects lead to an overestimation of causal influences as compared with a classical setting. And we can be much more general here. So we can prove that like every pure entangled state can generate correlations that violate these classical bounds. So showing that this is like a generic feature of quantum correlations. And more than that, we can use that as a witness of incompatibility between observables, because we can prove also that every pair of incompatible rank 1 projective qubit measurements, we always can find a state that if we measure this state, it's going to violate this classical bound. More than that, now we can ask, okay, if the classical bound is not good enough in the presence of quantum effects, can I derive quantum causal bounds? And the answer is yes. So now we can use the structure of Hilbert spaces and so on of quantum mechanics and derive bounds that are valid even in the presence of quantum effects. And why this is nice? Because now we have the first quantitative causal inference tool. Like if you have data and you don't know if quantum effects are present or not, you can just employ this quantum bound that you have the guarantee that they should hold also for quantum effects. And this is illustrated in this plot here. So if it's just a cut of the probability space, this blue region here would be the region where the classical bounds would be positive. So all these regions here. In red, it's the region where the quantum bound would be positive. And in these black lines here, it's the region where generalized probabilistic theories that go beyond quantum theory would also be positive. So this is very nice because we see a gap between these 3 levels, between classical and quantum and post-quantum. And why this is nice? Because this is showing us that all these ideas that we had from the correlational level, for example, for informational principles for quantum mechanics, we can also try them at the interventional level. So in principle, there might be some causality principles that explain why we cannot violate Bad inequality beyond a certain level, okay? So this is somehow contained here in this picture. Okay, so to finish, let me see how I'm going with time. I think it's okay, right? I'm almost finishing. We did a very nice experiment with Fabio Chiarino in Rome, where we tested for the first time this new witness of non-classicality. So here it's the experiment. We have a source of entangled states. So like these photons, they are entangled in polarization. One of the photons is sent to Bob, and Bob is going to measure his system. The other photon is sent to Alice, and in Alice's side, we have two things. We have her measurement apparatus that's going to measure the photon in a given basis, but whether she's going to measure or not in a run-to-run basis of the experiment, it's decided by a quantum random number generator. Depending on the value of this bit here, she's either going to measure her system, or via this optical switch, she's going to throw away this photon and decide the value of the outcome A. She's going to intervene in her system. So this was a very smart solution that they found to implement in a run-to-run basis, like whether to implement measurement or intervention in their quantum system. And here are the experimental results. So in thread, we have what we would get from the classical bound. So here I have observational data. So the data that it's entering here in this red curve, it's the data from when Alice did the measurement of her system. And in green here, it's the data when she did the intervention in her system. And we are just computing the A's. And we see that when we do intervention, yeah.
Can I ask you something? So
sure,
the violet dashed line that goes from the logical OR in Alice to Bob. So this is what, so when Alice makes a measurement, so the outcome of her measurement goes through that violet line through Bob's station, right? And with that, he decides which, so she sends her measurement outcome, right?
Exactly, because Bob, he needs this outcome to decide what he's going to do in his own lab. So because of that, we have this long fiber here, because the photon that Bob is going to measure, he has to wait until this bit of Alice has arrived in his lab. Because we have this temporal correlation,
And when she doesn't make a measurement, when she has to throw away her system, then you make like a logical OR there. Why is this logical OR? What is that doing there?
Well, because like Alice, she doesn't tell Bob if she's doing an intervention or not, right?
Sure.
So like independently of what she's doing, she has to send this bit, her outcome bit, to Bob. And then because of that, we have this logical OR here. That is just sending,
But what I mean is that when she doesn't make a measurement, like what is it traveling from Alice and Bob through that? What is that travels? Well, when she makes a measurement, it's her measurement outcome what travels from her to him. And when she doesn't, what is it that goes?
Then it's whether she forced her system to be in the system in the bit 1 or 0.
Oh, okay, like I see. She always sends 0 or 1. It's just that sometimes this is artificially chosen by her or comes from the measurement, from the quantum measurement. Okay, thanks. Okay, thank you.
And then you see that like we have a violation here of this causal bound, right? Because this green line, it's like almost 0, and this in the classical model would imply that we have something that it's positive. And here is just another experiment where we see again this gap between the quantum interventions that it's in green here and the quantum and the classical bound that it's in red. And the nice thing here, it's in this picture, it's the quantum bound, right? So this is what the our new quantum bound for causal influences would tell us. So it's telling us that like even if we don't do interventions, because here we are looking really at the observational data, it's telling us that the quantum causal influence should be positive, right? So it's showing that this quantum causal bound, it's also useful. Okay, so nice that I didn't lose my connection again, so I can conclude. The 4 main messages are these: causal structures beyond Bell, they are quite rich, even like simpler causal structures as compared to Bell. They give new results, and they remain yet almost unexplored. the instrumental causal structure leads to a new and stronger form of non-classicality. And this is very important because instrumental scenario contains the Bell scenario as a particular case. Not only it has these foundational consequences, but also can be applied to randomness certification and extraction with key rates that in some regimes are even better than what was known before. And here is the key message, and I really like this one. Bad inequalities are not the only signature of non-classicality, of the mismatch between classical and quantum descriptions of causality, because quantum correlations, they can violate these causal bounds even in scenarios where at the correlational level, everything would look classical. So indeed, what we have here, it's a new witness of non-classicality. Okay, so let me give a few words about things that we are doing or that we plan to do or that we plan that someone would do. And the first one is the most paradigmatic communication protocol in quantum information is nothing else than an instrumental scenario. This is just amazing. Like if you take a teleportation protocol and you think a little bit about it's, so what is a teleportation protocol from this perspective? We are imposing to our experiment the instrumental causal structure, where now two nodes are quantum. The source between Alice and Bob and the instrumental variable, because now the qubit that Alice wants to teleport to Bob is the instrumental variable. So, I mean, can it be that we have a strong connection and we can use like quantifiers of causality to somehow connect this with the fidelity of teleportation or things like that? So we are working on that. I don't have an answer yet. The second one, I think it's very nice because we are working now on quantifying quantum causal influences, right? Like not only between classical variables like A and B, but now also between quantum states. So what is the effect of a quantum state over another quantum state? And I think this has a lot of interesting applications. So let's say we have a quantum simulation of a complex molecule, and we would imagine that like parts of this molecule will have some causal effect over others. Can we use these causal bounds to understand that? And another nice application is like, what are the cause and effect relations in a quantum computer? So like part of my algorithm will affect other parts of my algorithm. And this becomes very clear if we move to this measurement-based model of quantum computation, because there we start with a highly entangled state, we measure some of the qubits, we get outcomes, and depending on these outcomes, we change the base that we are going to measure the next qubits in our highly entangled state. And in the end, we have like our computation encoded in the qubits that we didn't measure. So this is just a measurement-based quantum computer is a generalization of the instrumental scenario, where now I don't have a single instrumental variable. I have now many qubits, many instrumental variables that will affect the measurements that I will perform later to perform my computation. So can we learn something new about quantum computation using this quantum causal model? I think yes, but I just don't know yet. Finally, and this is the thing that gives me shivers because I find really exciting. So Pearl, he in his last book, the Book of Why, he defined what's called the ladder of causation. So we have three levels that we can associate to learning. The first level is the level that we are today before machines. We are at the association level. We are just looking into patterns in the data. We are looking at the correlations between parts of the data. Today, we talked about the interventional level, where we not simply see, we also do something. We interact with our system. And the next, it's what he calls the counterfactual level, where we construct models, and from these models, we can conclude something about our experiments. Just imagine, like without the need of actually observing or doing anything. And there is this very nice paper that came out this year where they proved the following. So we know the universal approximability theorem that guarantees us that if we have a powerful enough neural network, we can basically simulate any function. So any data that we give to a computer, to an algorithm, if this algorithm is powerful enough, it's going to be able to find a model that reproduces that data. But then in this paper, they proved the following. An arbitrary, complex, and expressive neural net is unable to predict the effects of interventions given observational data alone. So what they are proving here, it's very similar to what I proved to you. We can have something that at the observational level, we can explain well with a classical model, but at the interventional level, we cannot anymore. And what they are showing here, it's like for machine learning, like in the sense that like there are many different correlation level machine learning models that lead to different models at the interventional level. So this is very fundamental and very fresh. And to conclude, I learned today, just reading the news, that instrumental scenarios just got a Nobel Prize. So you can read more about, but these two guys, Engrist and Imbens, they got their prize for their methodological contributions to the analysis of causal relationships. And if you look, their scholar, one of their most citable and famous papers are exactly about using instrumental variables in the field of economy. So, I mean, it's a very hot topic, and we are just starting to understand its effects in quantum physics. And with that, here are some references of things that I talked about today. Many of these papers are in collaboration with Leandro. And I'm very sorry for my connection, but I hope you could get the message. So thank you a lot.
So thank you very much, Rafa. I guess we can applause, please, to the speaker, right? Yes. Thank you. This has been very, very instructive and clear. You managed to convey the message even with the little interruptions in the connection. No problem. Congratulations on the fantastic results on the intervention, on the experimental implementations of interventions. This is really, really nice stuff. Well done. This is really interesting. Congratulations on that, Rafa. This is very nice. So I guess if there are some questions, like always, I give priority to the juniors too. So if there's some student or some young postdoc that wants to raise her hand and ask some basic question, please, this is the time to do it. I can see some hand raising somewhere. Who is it? Is Renato? Yeah, it's Renato, I think. Yeah. Okay. Yes. Please, Renato, go ahead.
I don't know if it's working or not. Can you listen? Okay, I'm listening myself around. So I have I have 3 questions, but I forgot one, so I'm gonna just ask 2. In the experiment, were loopholes closed? Were there any loopholes to be closed? And if so, were they closed?
Yeah, so we are not, this is a very interesting question. So let's think about Bell. We have 3 main loopholes. We have the detection efficiency loophole. We have the locality loophole that they were closed. And we have one that in principle, it's hard to close, that it's the measurement independence loophole, like the free will assumption. Here, it's basically the same, with the difference that we don't have the locality loophole anymore, because it's a temporal scenario. I don't need to put these 2 guys in very large distances, because like what Alice is doing is it's affecting what Bob is going to do later. So in a sense, we don't have to care about the locality loophole. But the other 2, they remain, that it's the detection efficiency loophole that we don't close. So we are not using superconducting detectors here. The detection, if I'm not wrong, it's around 30%. So it's way below what we should have to close this loophole. So we are doing the fair sampling assumption too. And the And the free will loophole, well, I mean, we cannot close. So this is a assumption that it's always there. Yeah.
Okay, thank you. And my second question is about the neural net reference that you just showed in the end. Could you explain it a little bit in more detail? I don't know if you read the original paper or not, but
Parts of it, it's very long.
okay, but I would just like to understand like what type of interventions that are not explained by a complex neural net, or is it like really general for all types of interventions?
Well, I mean, for showing that, they only need to find the counter example, right? And I mean, the tools that they use, they are quite complicated. The proofs are long and so on. But the basic idea, I think it's very simple. That the point, like what they do, it's a purely classical. There is nothing quantum there. But their point is this: like what a machine learning algorithm is doing. He's taking this data here, that it's observational data, P of AB given X. And basically what the machine learning is going to do is to find this model here. He's going to find like response functions of A, given X and lambda. He's going to find some response functions for B, and he's going to sample over some probability distribution of P of lambda. And this is what the neural network is going to do, simply that. But the point is that having this model for the observational data does not lead to the correct models at the interventional level. And I mean, this is a bit trivial in a sense, because what is showing is this, that like a model at the observational level can lead to many different models at the interventional level. So discovering a model at this level here, that it's what our machines are doing, say nothing to us about this other level here. But this is crucial, because what we want is our machines to be able to say something about this level. We don't want our machine to just say, look, if I see X, I can predict that the probability of Y is something. The machine should be able to do something more. If I do X, what is going to happen? And this is what the machines at least at the current level, they cannot do. Okay, so I mean, it's easy to explain, but it's very hard to prove.
Okay,
so I take the train to ask you, because I was going to ask you a question. Thank you, Renato, for the nice question. I was going to ask you about this, right? Like you said, so if I understand correctly, these interventions, they change the mechanics, the underlying mechanics of the model, right? So they change some part of the inner dynamics there.
They locally change the variables that you are intervening.
Change the variable, right? And so they kill part of the dependencies, the ones that come to the variable on which you're intervening, right? And so in a sense, it's expectable that a machine that learns to generate samples from some observations, then you change the model, and now the dynamics that the machine kind of learned are no longer valid in a sense. But however, I agree with you that it's conceptually very deep, the no-go, like it's conceptually very deep.
Yeah,
it's very nice.
So I mean, I think it's really like if you agree that that learning algorithms should go beyond the correlational level, then we should think of how to integrate these two levels. How can I take like what I learned from one level to at the correlational level to the interventional level?
Right. So generative machine learning cannot learn causality relations. That's more or less the take on message.
Yes, that's the message. Yeah. Yes.
Okay.
And I mean, this has consequences to quantum machine learning. I think this is the part that I'm really interested, like because quantum machine learning is really at the correlational level yet.
Okay.
But so can we somehow integrate this new level that's the interventional level? Like, can we use data from interventions in quantum experiments, like to somehow improve our model?
I see. Is there any other question, guys, over there? Somebody else?
Question.
Renato.
I remember what my third question was.
Right,
when you show the comparison of bits extracted from this protocol and CHSH, protocol in an application. The difference wasn't that stark, but how different are those two in terms of cost of computation?
Okay, so like why this works. There is a very clear reason why we have this region here. If you think of how many bits you have to put in and how many bits you get out, so let's look here. In the Bell case, we need the two sources of input bits, one for Alice and one for Bob. So in the instrumental case, we only need one because the only source of randomness here, it's the inputs of Alice. And what Bob is using as the randomness for himself are the random bits that Alice is generating by measurements on a quantum system. So here it's like the reason why we should expect a gain of the instrumental in comparison with the Bell case. Like we have to put less bits in to start with. And the other, so like if you compare now the advantages, well, I mean, in a certain sense, the instrumental scenario is simpler to implement because for a Bell scenario, you have to guarantee that you have this space-like separation between Alice and Bob. And in this case here, we don't have that anymore because it's a temporal correlation. So in principle, Alice and Bob, they could be even in the same lab and still like use this causal structure to guarantee that they have random bits. So, I mean, there are many subtleties here, but in principle, the instrumental case, it's simpler to implement in the lab.
All right, this has been a fantastic talk, Rafa. Thank you very much. I guess, yeah, it's already time we finish. You've been speaking for 1 hour and 15 minutes. So this has been really instructive and it's very exciting. It's very nice to see that there are still conceptual news coming out from this type of questions related to the instrumental. Like it's really nice to see that there are still experiments coming out. So congratulations on that again. And thank you so much again to you, Rafa. Thank you guys for coming to the auditorium. From my side, I think it's been good. It's been great. Like the sound, the video. Thank you, Ingo, again, once again for the technical arrangements. And I think this was very nice. Yes, thank you.